Okay, this question is about gravitational potential energy and escape speed. So, escape speed is a term that we use for a particular situation where we say we want to have a rocket or a projectile or something that starts from the surface of Earth or the surface of some other planet or object with enough velocity. We're going to give it enough initial velocity that it can make it infinitely far away from Earth. So if we don't give enough energy, it'll sort of go out some distance, it'll run out of speed, it'll turn around, it'll fall back down. But if we give it enough energy, then it can keep going forever. And so escape speed is the term for the minimum speed that the projectile needs to be able to do this. So this is an energy conservation problem. Basically, we're saying we have some initial situation here. So my initial situation is here at the surface of the Earth, and my final situation is here out infinitely far away from Earth. And I guess another way to think about this is in our initial situation, we're a distance r from the center of the Earth, that's the radius of the Earth. And here, out in our final situation, r is infinity. And we should remember that our gravitational potential energy for this object, this projectile, is negative big G, mass of the Earth, mass of the projectile, over the distance from the center of the Earth. So we're going to set up conservation of energy. Basically, our initial energy, total energy, has to equal our final total energy. And let's say, since we're looking for the minimum speed that we need to go out to infinity, we're looking for the case where our final kinetic energy is 0. If we gave the rocket more initial kinetic energy, then you'd still have some kinetic energy left once you got to infinity, but we're just looking for the minimum speed we need. Second, let's note that when r goes to infinity, gravitational potential energy then goes to 0 because r is in the denominator. So this term is also going to be 0. So our escape speed is going to happen when our kinetic energy is equal to our negative potential energy. So 1/2 mv initial squared equals negative ui, so g mm over r. And here, this distance r is the radius of the Earth, and this big mass here is the mass of the Earth, and the little m is the mass of the projectile, which it turns out is going to cancel out. So the escape speed, it's going to be the same speed for any projectile no matter what the mass is. So we just need now to solve for vi. So vi equals square root of 2g mass of the Earth over radius of the Earth. And you can look up these values. They're in your book, or you just Google them. G is 6.67 times 10 to the minus 11 Newton meters squared per kilogram squared. The mass of the Earth is 5.97 times 10 to the 24th kilograms. The radius of the Earth is the 6.37 times 10 to the 6th meters. And if you plug those all in, you'll find that our escape speed from Earth should be 1.12 times 10 to the 4th meters per second. And, escape speed is just a term. So, now that you know what that means, you might want to calculate the escape speed for other objects, planets, moons, comets, and you can do that. Okay.